So what is effect size? This p-value or this hypothesis testing, whatever we have done, okay, it just measures whether whatever you have tested, whether it's statistically significant or not, the p-value that we have in the hypothesis testing. So depending upon that, whether it's more than critical value or less than critical value, depending upon that, it just tells us whether it is whatever we have done, whether medicine 1 or medicine 2, whatever the recovery time is, whether it is statistically significant or not. It just tells me that. Okay, it is less or more, or both are equal or not equal, it just tells me that, but it doesn't tell me the magnitude of that difference. Okay, and that's where effect size comes into picture. So the p-value only tells that whether it is statistical, the test whatever you have done is statistically significant or not. But effect size measures that how much of effect is there. Because of medicine 1, if the recovery time is very less than medicine 2, so it captures that magnitude of the effect or the difference. So this effect size captures the effect. Okay, how much of effect is there? How much of effect is there? It just tells that there is some difference, whether it's significant or not. It just measures that p-value, but this tells that whether it is how much, what's the magnitude. So it captures the magnitude. Okay, also it gives us a standardized magnitude. Okay, it standardizes the value so that we can compare the values, as in correlation, right? We can compare the correlation based on the correlation coefficient. We can compare the data from across tests, across different tests and across different sample sizes. Maybe coming, so for example, if I'm comparing the height and age, whether height has impact on age or not, or the mean height of two groups. Okay, and I'm comparing mean salary of two companies. So they are across different samples and different sample sizes and across different metrics units. One is in centimeters, one is in rupees or dollars, whatever is there. But I can compare, since this effect size is standardized and the magnitude is captured there, I can compare two effects. What was the effect across tests or across sample sizes? I hope that makes sense. Okay, so the larger the impact, okay, means more the effect size. For example, there is a formula for this that is called Cohen's D formula to measure it. Okay, and this is equal to, okay, it is for comparing, for example, it is for comparing mean of two groups. In this only, mean of two groups, mean of two recovery times of two medicines, mean of two groups. So what is the formula? X1 bar or MM1 minus X2 bar MM2 mean recovery time from the sample mean of the two groups divided by pooled standard deviation. So this is what makes it, this is the standard deviation. So let me write it. This is your pooled standard deviation. Pooled means which is pool of both the standard deviation, pooled standard deviation. And these are sample means. And the pooled standard deviation formula is, so it has also got a formula. This pooled standard deviation is equal to square root of n1 minus 1 s1 square plus n2 minus 1 s2 square by n1 plus n2 minus 2. So this is going from, I think, from degrees of freedom, n1 minus 1, n2 minus 2, or the standardization, or that Bessel's correction. Okay, we can check that. So this is your pooled standard deviation formula. So we plug this in here. So for this medicine also, we'll have the sample size for the mean recovery of two, mean recovery time of two medicines. We have the mean from the data that we have. We can calculate the sample mean of the two medicines. We can calculate the pooled standard deviation also, and this pooled standard deviation makes it standardized because both the units will be same. This is square root of variance. Standard deviation is the same unit as the thing that we are measuring, right? If this is in centimeter, this will be in centimeter. This is in rupees, and this will be in rupees. Okay, and this is your unitless. And this is your pooled standard deviation formula. You have all the values. You know the sample size, you know the sample standard deviation, everything, you plug it in here and you will get a value for that. Okay, and generally this value varies from 0 to 1. And let me show you graphically. For example, if there are two samples, okay, two samples, and let me draw it. So there are two samples. One sample is like this and another sample is like this. So this is your mean, this is your mean. So the distance between these two, if this is small, okay, this is small here, so this is your small effect size, small effect size. The mean is not too far, then whatever is the impacted, both are almost same. This x1 and x2 are both almost same, means the effect is small. The difference is small means effect is small. So there can be one way it can be like this. The other way can be, it can be like this is small. Similarly, there can be some difference. This is red one, and this is, there can be some, it can be somewhat far. So if you see now, okay, now this is your effect size. This, the difference, the distance between the means here, this is your effect size. This is what is measuring, because that is what is being captured here in the numerator. Okay, so this is your medium effect, more than small, medium effect size, and either this can be like very far. I can have the red sample like this and the blue sample like this, no overlap. Okay, quite far. And this we can say that this is your large effect size. This is your large effect size. The means are going farther and farther. And if we see in terms of Cohen's d formula, so this can be, say for example, this is like just 0.2 small effect size. Okay, d is equal to, here the d can be equal to 0.5, and here it is like, say for example, d is equal to 0.9. Okay, so depending upon the Cohen's d value, we can compare the two effects and the effect size. The distance between the closer they are, the less is the effect size. Okay, because of this. And if they are in between and the farther they are, the larger is the effect size. Okay, I hope that is clear. For example, I'll give you just quick example that if I do a study on patients which measures the effect on the same medicine line, okay, effect of a medicine and a placebo. Placebo is like, you just give that, it's not a real medicine. You just tell person that this is a medicine, but it's not a medicine. That's what is a placebo. So you give one control group, you give a placebo, other control group, you give a real medicine, and you compare the improvement. And then you find out that the p-value is significant, that you accept the null hypothesis that p-value is 0.05. It is greater than. Okay. So you reject the null hypothesis and you say that there is some difference between the two groups. Okay, the placebo and the medicine, there is some difference, they are not same. And then you try to find the magnitude of that effect. What is the effect of the medicine? Is it better than the placebo or not? Okay, if the effect of the medicine is very small, then the effect size will be small. If the small, then we calculate from the Cohen's d formula, small effect size. If it is 0.1, say 0.1, then we can say that the drug didn't have any, had minimal effect. It was just a random, by chance it happened. Okay, but if the effect size is large effect size, say for example that is like 0.9, then you can say that the drug produced the substantial result. Okay, whatever the result was there, it was because of the drug really being, okay, better than the placebo, and the drug produced the substantial improvement in the patients. And this is the p-value just tells that whether it is significant or not, and after that we measure the impact, and that will come from your Cohen's d formula, which will measure your effect size. I hope this is clear now.